do you think would happen if you dropped like the heaviest object you can think of and the lightest object you can think of at the same time from the same height? Which one's gonna hit the ground first?
This is like one of those really obvious questions. Like, I think they're gonna hit the ground at the same time. No, that's stupid. No. Shh. No, you can't put this in your video. No, delete it. No, delete it.
Are you gonna answer the question?
No, the light one's gonna float and like, well, not float, but like it's gonna go down like this. Woo, like a feather. It's gonna fall down.
If air resistance is negligible.
What?
If air resistance like doesn't count.
Oh. Did you say that before?
No.
Oh, okay, well, I don't know.
Just give me an answer.
They're gonna hit the ground at the same time.
Is that your final answer?
Yeah?
You sure?
No. I don't know. Nora.
Okay, we're talking about gravitational force fields today. We all know what gravity is, give or take. We all have a basic concept of it. So, us on Earth, it's what keeps us on the ground. And at nearer surfaces, it's like about equal to 9.8 newtons per kilogram is the force it acts upon us. But it's a force field, so it acts at different forces, different distances from the mass, the Earth. So like, an object way out here, it still has the gravity of the Earth acting on it, but it's much less than 9.8 newtons per kilogram. At the beginning of this video, we asked Natalie Tassell what she thought would happen when two objects of different masses were dropped from the same height at the same time. Now we're about to figure out what's going to happen. So here's object 1, assume it is 1 kilogram. Object 2, assume it is 10 kilograms. So they're dropped and they're going to hit the floor. So this distance is 2 meters. So we'll draw 3 body diagrams on them. This one is going to have a force of 9.8 newtons per kilogram times 1 kilogram. So that's going to be 9.8 newtons. And then this one, which is 10 kilograms, is going to have a force of 9.8 newtons per kilogram times 10 kilograms. So it's going to have 98 newtons. So we know that F equals ma, which can be switched around into A equals F over m. And we also know that delta x equals initial velocity times time plus 1/2 acceleration times time squared. So for object 1, delta x equals initial velocity times time plus 1/2, and we're going to plug in F over m for acceleration times time squared. So that's going to be, the delta x is going to be, we need to define our world. This is going to be the positive direction. So delta x is going to be 2 meters. The velocity, the initial velocity, since it's at rest, is 0. And then you add 1/2 force, which is 9.8 newtons, divided by mass, which is 1 kilogram, times time squared. Then, to solve for time, you get 2 times 2 meters times 1 kilogram divided by 9.8 newtons per kilogram. and then the square root of that equals time. Okay, so time equals 0.639 seconds. So this is for object 1. So let's try and figure out what time is for object 2. Delta x equals initial velocity times time plus 1/2. We're going to do the same thing we did earlier. Force divided by mass times time squared. This is still 2 meters. Initial velocity is 0 plus 1/2 force, which is 98 newtons per over newtons per kilogram over 10 kilograms times time squared. So to solve for time squared, we get, or to solve for time, we get 2 times 2 meters times 10 kilograms divided by 98 newtons per kilogram. And then the square root of that equals time, which equals 0.639 seconds. Therefore, since the times are equal, we know that they're gonna fall at the same time. They're gonna reach the ground at the same time, so the mass didn't have an impact on them. Okay, now I'm gonna demonstrate this by dropping a rock and a crumpled up piece of paper.
Ruby.
3, 2, 1.